In this video, I am going to introduce the elementary particles quarks. They are the ultimate constituents of hadrons. What are hadrons? We know that particles can be classified into two, hadrons and leptons. Hadrons subject to strong interactions while leptons do not subject to strong interactions. In 1964, Murray-Gell-Mann and independently George Zweig proposed the quark model. According to them, hadrons are built up from a limited number of fundamental units called quarks. We know that every particle has an antiparticle. Each quark has an antiquark associated with it. There are 6 different types of quarks, or we usually say there are 6 different flavors of quarks. Flavor is a word used to distinguish between different types of quarks. 6 flavors of quarks are up quark represented by U, down quark represented by D, strange quark represented by S, charm quark represented by C, top quark represented by T, and bottom quark represented by B. Up and down are the most common types and they are generally stable. Nucleons are composed of these up and down quarks. Top is the heaviest quark. It is generally observed in high energy collisions, while up and down are the lightest quarks. Heavier quarks generally decay into up and down quarks. Now let us consider the properties of quarks. The most striking observation is that electric charge and baryon number are fractional for quarks. Each quark has a baryon number 1 by 3 and a half integral spin number. Look at the table. You can see that up, charm and top have a charge of plus 2 by 3 of electric charge E, while the remaining quarks have a charge of minus 1 by 3 of E. Strangeness number is represented by S and strange quark have the strangeness number of minus 1. All others have 0 strangeness number. Charmness is represented by C and its value for charm quark is plus 1 and so on. Coming back to hadrons. Hadrons are again divided into baryons and mesons. Baryons are composed of 3 quarks while mesons are composed of 2 quarks. Nucleons belong to the group of baryons. Now let us look into the core composition of nucleons. A proton is composed of 2 up quarks and a down quark. The up quarks have electric charge of plus 2 by 3 of E, while down quark has the electric charge of minus 1 by 3 of E. Adding up all these charges we get plus 1. That is, proton has a charge of plus E. About the baryon number, since there are 3 quarks in a proton, the total baryon number will be 3 times 1 by 3, that is plus 1. From the earlier slide, we know that both up and down quarks have strangeness value 0. So, a proton has 0 strangeness number. Similar is the case with a neutron. A neutron is composed of 2 down quarks and a single up quark. Here we get total charge 0 and baryon number 1 and strangeness number 0. Another look into the spin and charge of nucleons. This slide explains the quark composition of antinucleons, that is antiproton and antineutron. Next is meson. Mesons are made up of 1 quark and 1 antiquark. A pi plus meson is shown here. It is composed of an up quark and a down antiquark. Here the total charge is plus E, baryon number is 0 and strangeness number is 0. There was a serious problem associated with the idea that baryons are composed of quarks. For instance, consider a proton. In a proton, there are 2 up quarks and a down quark. The presence of 2 up quarks with all identical properties in a proton violates the Pauli's exclusion principle. Since quarks are half integer spin particles, they are fermions. Being fermions, quarks ought to be subject to this exclusion principle. To get around this problem, it was suggested that quarks and antiquarks have an additional property called color. This additional property of some kind can be manifested in a total of 6 different ways, just like an electric charge. Electric charge is a property that can be manifested in 2 different ways, which have come to be called positive and negative. In the case of quarks, this property became known as color, and its 3 possibilities were called red, green and blue. The anti-quark colors are anti-red, anti-green and anti-blue. According to color hypothesis, all 3 quarks in a baryon have different colors, which satisfies the exclusion principle. Similarly, an anti-baryon consists of an anti-red, anti-green and an anti-blue quarks. This slide explains the color associated with quarks in nucleons. A meson consists of a quark of one color and an anti-quark of the corresponding anti-color. This has the effect of cancelling out the color, and we say mesons are colorless. To conclude, we can say that quark color is a property that is significant within hadrons but is never directly observable in the outside world.